Thanks everyone for coming. For our first talk, we're very happy to have Eva Silverstein here from Stanford to tell us about M-theory compactifications and de Sitter space.
Thanks, John, and thanks to the organizers for this great meeting. So indeed, I'll talk about some recent work with Bruno De Luca and Gonzalo Taroba, and if there's time, some ongoing work on a sort of related subject involving machine learning. We had checked that it goes forward, but now it's not. Oh, sorry, just delay. Okay. So as everyone knows, the cosmological constant was discovered 20 years ago, one of the most amazing events in my career, I'd say. And we're still trying to understand it. A major goal we all share is to formulate it fully in quantum gravity, and I'll take that to mean string or M theory. And that already led to a number of weakly coupled large radius de Sitter and inflation models with some observationally testable signatures. And this is always at the model dependent level, but still it's useful, and it's contributed not just to testing those models, but also to a more systematic analysis of early universe data generically. I'd say we have a start on the upgrade of ADS-CFT to cosmology, but not a complete framework for that yet. And there's much more to learn, particularly, well, on all of these fronts, but particularly on the latter front. In this talk, I'll specialize to a particular class of compactifications, which have some nice properties. So this will start from the M theory, or at low energies, the 11-dimensional supergravity limit of string M theory. And we'll compactify on a finite volume hyperbolic internal space. It'll be dressed with warp and conformal factor variations, so I'll say deformed. And this automatically generates an interesting scale of Casimir energy, and adding one ingredient to that, one stress energy ingredient by hand, 7-form flux, yields an immediate volume stabilization mechanism with positive cosmological constant. These manifolds have a very useful other property, which is well known mathematically, called rigidity. So if you think about how we do compactifications, we start from some higher dimensional limit of the theory, and we compactify on a manifold. The Einstein term in the higher dimensional theory descends to part of the potential energy in 4 dimensions. Let's call it the curvature potential. And that curvature potential in these negatively curved spaces, which are generic types of manifolds, that curvature term is gapped when it comes to deformations of the metric. All deformations of the metric, aside from the conformal rescaling, which is usual in gravity, has a negative gradient term, but that negative gradient term, which would apply to any compactification, even a torus, is not a real instability. It's instead stabilized by the warp factor, as was explained clearly in a paper of Mike Douglas in 2009. So the combination of these two features, all these features, makes these compactifications particularly well suited for doing physics from M theory. So just to belabor the motivation a little bit more, we do have a lot of evidence for positive potential energy in the universe, and so far, at least, only constraints on supersymmetry. So it's natural to work with the leading positive potential terms in the 4-dimensional effective potential, which in string theory limits actually starts with a d minus d critical term. But even if you turn that off, and it's not there in this M theory limit, the curvature term is, as I keep saying, generically a positive potential term because of the fact that negative curvature is generic among finite volume manifolds. And so just that genericity is a good motivation. And it does have these properties that make it in certain ways simpler to analyze. And for me, that's part of the motivation too, because of the goal of developing this business of uplifting ADS-CFT to cosmology, where we want to extend the entropy counts and such things to the cosmological setting. So simplifying these models helps with that. Okay, and over the years, this is not a new idea to consider such internal spaces, and over the years, many works have appeared showing how such backgrounds are connected to the rest of the string landscape. Okay, so enough for the motivation. Let me get into it. I've already said what the setup is. and this rigidity property. And now let's start again as a warm-up, as a sort of motivational warm-up. Let's start with the homogeneous level of the potential energy. Will include field variations, including the all-important warp factor variations shortly. But at this level, we have a curvature contribution, which is positive. We have Casimir energy, which it will be dominated by bosons and be negative, and a flux contribution, which is positive and scales like the quantum number squared divided by the volume squared, all times the usual overall Einstein frame conversion type factor. And what you can see here is that this structure gives the required three-term structure to stabilize the volume. As usual, we have the feature of string theory and M theory that all the potential energy sources go to zero at large radius or weak coupling. And so the simplest way that such de Sitter models can work is through a three-term structure in those directions. And that's the essential complication of the thing. Okay, so this is the point. The point being that the Casimir energy, which sits in the middle of the two positive terms in this expansion, 1 over the curvature radius L, sits in the middle and has a negative sign. So it produces the important negative contribution to the potential that's always required in such constructions. And in previous models, this role has been played by O-planes or non-perturbative quantum effects. This is a perturbative quantum effect in this case. Okay. We can calculate the Casimir stress energy. I won't belabor this for a short talk, but both studies of negative curvature spaces internally and Casimir energy as a stabilizing force is previously in the literature, including in these papers. As you know from the Casimir effect, it's a kind of infrared effect in a finite cavity, and so it's dominated by regions of the geometry where circles become relatively small. We'll keep them still parametrically larger than the 11-dimensional Planck length. But such small circles are a dime a dozen in hyperbolic manifolds, which typically have cusps with a local metric that is of this form, with a cross-sectional torus, which evolves radially with some spatial direction y in this manner, which is just a slice of Euclidean ADS. It's a hyperbolic space, but again with this compact cross-sectional T6. Moreover, there's a nice generalization of Dane filling, where you smoothly cap off the cusp, leaving the smallest circle finite, that extends to the higher dimensional case. Dane filling applies to 3 manifolds, and Anderson's generalization of that in the math literature extends it to higher dimensions, filling it in with an Einstein manifold. Okay, so that's the setup to have in mind in terms of where the Casimir energy is most strong, and with that we can calculate this Casimir term in terms of the relevant parameters: the curvature radius L, the Hat's mean in units of the 11-dimensional Planck length, the size of the smallest circle that I just described, and the cross-sectional shape of the torus and the number of cusps and the ratio between the total volume and the curvature scale to the 7th power. Okay, so I was motivating with the dimensional reduction in the form of the 4-dimensional potential. There's a really beautiful paper by Mike Douglas in 2009, which spells out what we really mean by the off-shell effective potential in 4 dimensions. And the point is to be careful about the constraints of general relativity, which come from integrating out the warp factor, this e to the 2a factor, which we'll often call u, multiplying the 4-dimensional component of the space-time. And that has no business in the potential energy in 4 dimensions, which should just be a functional of the internal fields. And the way that works is that you have to integrate it out. It's all its internal components, solve the constraint. That constraint equation, the equation of motion for u, takes a very beautifully simple form in the compactification down to d equals 4, meaning it's a linear equation. This c ends up being given by the curvature of the four-dimensional component of the space-time. In our case, since we aim for a de Sitter solution, it's the de Sitter curvature. So the four-dimensional effective potential is given by this expression here, with the u's that you see in this expression obtained by plugging in the solution to the constraint equation, this Schrodinger-like equation here. So the upshot is that this expression is just a function of internal variables, the seven-dimensional metric, the potential form C6. And you can see effects of the warp factor in this formula. Notably, as usual, it redshifts down regions depending on its value locally. So there's a u squared here. And also, importantly, it appears with this minus 3 del u over u squared, this gradient correction to the curvature term. So earlier I listed the curvature term, the Casimir term, and the flux term, and now I'm including this warping contribution to the curvature term that comes from the proper definition of this 4D potential. Okay, so there's a lot of, well, okay, also one can solve for the flux. I won't belabor that, but one can solve for that in a simple way, including the effects of any varying warp factor. There's a lot of physics in this whole framework of Douglas's. So I mentioned that it's a linear equation for the warp factor u. And what appears in the analog potential is actually minus the naive potential of the dimensional reduced theory. So what that means is that negative sources like the Casimir energy behave like potential walls in this analog Schrodinger problem. And the u, the wave function, screens those, so you don't get rampant instabilities. The most important example of that is the thing I mentioned briefly earlier, which is that if you think about the conformal factor rescaling any metric, again, for this point, it doesn't matter what choice of internal space you pick. But if you then rescale that manifold by a conformal factor and work out the new curvature term, you get the usual negative gradient contribution. But that's not the end of the story. This would look like a terribly deep instability, but it's not. And the reason is that when you properly integrate out the warp factor, that turns around. So you get a positive net Hessian in that direction. And in general, the physics that comes out of this analysis of Douglas has to do with the warp factor playing such a role of screening and otherwise turning around certain instabilities that would otherwise be there. Okay, so coming back to our setup, the kind of executive summary of the structure of the internal space, and I'll note some explicit examples shortly, is as I've sketched at a cartoon level here, we have a bunch of cusps filled by the Anderson-Dane filling. We have this net curvature term that I highlighted earlier. One combination of the equations of motion, now not just the warp factor constraint equation of motion, but also the equation of motion for the conformal factor, leads to this key equation highlighted by Douglas and Kalosh in 2010, which shows the sign of the net curvature term, as a function of the sources here on the right-hand side. So what you see is that where the Casimir dominates, this net curvature term is actually positive and vice versa. So Casimir is inhomogeneous. It's localized in these small circle regions of the geometry, and in the other regions, this net curvature term takes the opposite sign. Okay, so this is a important fact about the equations of motion. We'll come back to it. And so we can find explicit discrete parameters that enable us to keep this net curvature term overall quite small. And I'll show that also in explicit solutions in the cusp. Okay, so that's the strategy. We have in this three-term structure now the net curvature term, the Casimir contribution, the flux, which generally is generalized if we were to include F4. and the stabilizing effects of the hyperbolic Hessian and the warping transverse to this 1/volume direction. So basically these two slides are giving the sort of executive summary of the mechanism. Now let's talk a little bit more about this net curvature term. So Casimir energy is a quantum effect and the curvature is a classical effect. So one needs to understand how it is that they can compete. Part of the answer to that is that the circles can become very small, but one doesn't want them to become too small or else M-branes could start to wrap those circles. So, but there's also this degree of freedom in the net curvature. And so what we can do is ensure that the net curvature is small enough that Casimir with a reasonably small but not overly small circle compete. So that's the strategy. And more explicitly, here's how we can do that. I'm going to flash a set of very explicit hyperbolic manifolds for which these comments apply. But for now, let me just state it in words. We can start from some value of this ratio of the net curvature term to the naive curvature term. And if this ratio A is too large, we can decrease it by increasing the volume of regions that don't contain strong Casimir energy. That's a very easy thing to do. For example, in these manifolds, I'll show you, and it's a rather common thing in hyperbolic geometry. One can take a K-fold cover and then do a K+1 fold cover and have a very fine variability of the volume containing Casimir cusps compared to that not containing Casimir cusps. We can also make the cusp short or long and in that way change the fraction that contains strong Casimir energy. On the other hand, if A turns out too small, which is kind of a good problem to have, one can increase it by reducing the flux quantum number, which is also very, very finely variable in this kind of system, because it scales like the quantum number divided by the volume squared, or L to the 14th. Okay, so for all of this, it's important that we understand hyperbolic geometry well enough to know if these kinds of specifications make sense. And indeed, there are concrete classes of hyperbolic manifolds with very comparable cusp and bulk volumes, and even ones that have this very easy to handle form that I'll mention now. So there's this beautiful paper that actually came out in the course of this project, although the subject of hyperbolic geometry is very, very well studied in mathematics, and there's a great textbook to look at for the generalities. Anyway, there's a class of manifolds that makes explicit examples of hyperbolic spaces of the type we're interested in as a gluing of right-angled polytopes in hyperbolic space. So in our paper, we offered a kind of appendix spelling out how this works with depicting it in a lower dimension, but a very similar procedure, as they explain in detail in this paper, applies up through higher than dimension 7 that we need. So these manifolds have the properties that I described a slide ago. So I'll leave it at that, but just so you know, you can play with these to your heart's content if you're interested. And in general, another of the motivations for this whole thing is that indeed hyperbolic geometry is a very well studied and well understood topic in mathematics. The metric is known, and the boundary conditions involved in constructing a finite volume space are also known. So in that regard, it's actually easier than, say, Calabi-Yau, where you have to do some machine learning to find the metric, or as Shamit and Max and so on found it for K3, you can do some more intricate mathematics to find it. But here it's just trivially known from the start. Okay.
You're about 20 minutes in. So
okay. Okay, that's good. So with all that I've said, we can go back to the stabilization mechanism. This A appears in the stabilization mechanism that balances the curvature and Casimir terms, and the flux as well. And if you simply study these relations, you find that indeed there is a window where all the length scales are large compared to L11. The Casimir circle is smaller than the curvature radius overall, but much bigger than L11. This A, which we showed how to tune, is, decision models are not new, so that having such a control parameter is familiar. It's analogous to the D of the supercritical models, the W naught of KKLT that we've heard about already, although there is more structure there, as Arthur stressed. There's various topological quantum numbers in the Riemann surface compactifications and large volume scenario. So for us, this A is playing that sort of role. The last thing that I should make sure to get in before John tells me it's time is that within the cusp, so in general, the field equations in this space are specified by the local equations of motion and a boundary condition at the gluing of the polygons, of continuity of the fields and their derivatives at the gluing of the polygons. But deep in the cusp, the whole thing reduces to an ODE. And here's a sample solution which illustrates that indeed all the sources can compete, and that this parameter A starts out at a very modest value, less than 1, and then we can fine tune it with that prescription that I mentioned earlier. And here's just another picture of this ODE incorporates this Dane filling sort of prescription that I mentioned earlier. So there's a solution of the field equations that illustrates what I was describing more qualitatively in the previous slides. Okay, so with that, let's go to the second order fluctuations. And here, again, there are these helpful contributions from the rigidity and the warping effects. Here's just a proper presentation of the theorem about the rigidity that I already described in words. This is standard textbook material. And also here are the equations that go along with what I was telling you earlier about how the warp factor related to this field A turns around what would have been an instability for the conformal factor B. We were able to generalize this effect to show that an arbitrary, show more generally, once we do tune to small cosmological constant, that the warping contribution to the Hessian is universally positive. So there's a lot of lines of, well, there's a few lines here of analysis, but just to describe it in words, here we exploit the Schrodinger problem that I described earlier that is equivalent to the warp factor equation of motion. From that formulation, we can treat it like a Schrodinger problem. We can do things like take expectation values and look at trial wave functions and such things, and also simply pursue quantum mechanical perturbation theory the way you do in ordinary quantum mechanics. And in that spirit, what you find is that if you look at how the warping contributes to the Hessian, it's always positive. In our project, Bruno coined the term automathic. So if you learn nothing else from this talk, I would remember this term is very useful. And so in that language, the warping contribution is automatically positive. This thing with the conformal factor was not an accident. Okay, so I could go through the details, but I think we don't really have time.
Yeah, now you're dipping into question time.
I'm dipping into questions. Okay, so just finally, there's a trial wave function analysis that also supports this picture. But what we didn't do is a brute force direct calculation of the Hessian. And one could do more with numerics and so on that front. But all systems go in terms of these various analytic estimates giving positivity. Okay, there's yet another version of axiom monodromy inflation in this setup, just adding the four-form flux. And I want to stress that in that and in general, in such models, when it gets well past the Planck length, with a small effect of light fields, and that should be taken into account in such discussions. Here in an earlier example with Liam and company, where there was another realization of the phi to the 2/3 model, indeed, the evolution of the spectrum of light fields changes by only a factor of 10 to the 1/6, so a very unimportant factor. And I just want to stress that because the empirical tests of these types of scenarios are coming up, and we should be clear about the theory. Okay, so with that, I'll skip the machine learning idea, but happy to talk about it in the discussions and just head to the conclusion, which will come in a while. This is extra material for perusal as you wish. Here's the summary. I'll just leave it up and would be very glad to discuss anything with any questions. Thanks.
Great. Let's thank Ava for a very nice talk. I believe we have time for 2 questions, which seems like we have. Fernando, I think your hand was raised first.
Hello, Eva. Very nice question. A very nice talk, Eva. I enjoyed. Just a question on this scenario with these compactifications. Do you have a way where to put the chiral matter where the standard model will be? Has there
Well,
been?
I think that's a great point. One could start, sprinkling in things like Hojava-Witten walls and that sort of stuff.
But is there anything done already, or?
No, it took us quite a while to think through this at the level of just the inflation. One thing I should stress, that's a great question. I mean, short answer is we have not thought about that very much yet, but I think it would, I think that aspect would be similar to what is done in more familiar M-theory compactifications, if I'm not mistaken. One thing I want to should say about this by way of motivation that's kind of orthogonal to that is that these compactifications are uplifts of the ADS7 times ADS4 times S7 ADS CFT system. So part of our motivation was just that, was how do you get a de Sitter model that is as close as it can be to a known ADS CFT dual pair. And this is an example of that, where such an ADS CFT dual pair would have a positive curvature internal space and also the F7 flux. And by uplifting in the sense of changing to negative curvature, you get to this de Sitter. So in other words, there's applications to thinking about those kind of holographic issues independently of phenomenology, but certainly it's interesting to do the generalizations that you suggest for phenomenology, particularly at the string phenomenology meeting. So
that would be very interesting, I think, because it opens up a lot of possibilities that have not been.
Yeah, I think so. I've been thinking it's going to work in the same way it works in other cases that have been studied, but it's a good question to see what nuances there would be here.
Thank you.
So it seems like we probably don't have time for another question. So Artur, if you could bug Ava on Slack, I think that it would be best to move on. Let's all thank Ava again for a very nice talk. And then Liam, if you could try sharing your screen.